let's say that I gave you the integral from 3 to 7. And I want to give us a function that we can actually finish off the limit in case anybody wants practice with that. Let's go 3 to 7 and make our function two minus x squared. This is going to get messy, but we're going to be okay. So let's first start by writing this out as a Riemann sum. Generically, for our Riemann sum, thinking about getting some partial credit here, I'm thinking about the limit as n approaches infinity. In order for this to actually be equal, I'm going to take the sum, and each of those rectangles has a base and a height. So that delta x is the base of my rectangle, and the height, to use the book's notation, that's going to look like f of x sub I star. And we're going to go from I equals 1 to n. Now let's look at formula-wise that delta x and what f of x sub I star is. So delta x is always b minus a over n. So in this case, my b and a are those limits from the integral. Delta x is 7 minus 3 over n, or 4 over n. This x sub I star, I know that notation's a little bit messy, but that x sub I star has a formula associated with it that's probably worth memorizing. And I like to just call it x in quotations, because this is our generic x for our ith rectangle. This x as a formula is always going to look like a plus I times delta x. And that's going to be true whenever we have right-hand endpoints. If the question just asks us to write it as a Riemann sum, then we get the choice of left endpoints, right endpoints, midpoints, trapezoid rule, but right-hand endpoints make the algebra the simplest. So I always choose right-hand endpoints whenever I get the choice. That's going to mean that our x values, we're starting at 3, so that's 3 plus I delta x. And in terms of kind of where this formula is coming from, if I think about that interval on the number line from 3 to 7, and I'm just going to draw in some fake rectangles. Since we're using right-hand endpoints, the right-hand side of that first interval, I started at 3. I know that the width of that interval was 4 over n, which means I've gone, my x value here is 3 plus 4 over n, because that's how far I've moved over. When I get to my second rectangle, I've moved over 2 of the 4 over n's. And by the time I get to my ith rectangle, I started at 3 and I've moved over I of my 4 over n increments. Putting that all back together in our summation here, we're going I from 1 to n. Delta x was 4 over n. And then the function part gets a little bit messy, but the function was 2 minus x squared. So that's going to look like 2 minus x squared. And that x is coming from right here. So the x that we're popping in will make this look like 3 plus 4i over n. And if what we were asked to do was to write the Riemann sum, we're done. That's what it is. Now we can do some algebra to keep going, but that's the Riemann sum, so if that's what we're asked, I would quit. I want to write the Riemann sum and then take the limit to evaluate this area. First step, I know that I'm going to need 2 things for that Riemann sum. So we're taking the limit as n approaches infinity. I know I'm going to go from 1 to n, and my 2 pieces, I need f of x, I need delta x, and I need f of x star. So coming off to the side, or actually I'll just squeeze it underneath here. I equals 1 to n. That delta x, again, since I'm going 3 to 7, delta x is going to look like 7 minus 3 over n, or 4 over n. Our function, or if I'm thinking about x star, x star is going to be wherever we started, so in this case 3, plus I times delta x. Or I could write that as 3 plus 4i over n. And if that's the value of x, our function, which is 2 minus x, is going to look like 2 minus 3 plus 4i over n. This time, because I do want to actually find the answer to this limit, we're going to have to simplify the algebra so that we can take the limit. This is something that I talked about last week, but one of the things to know about summation and summation rules is that if we have a constant, we can move that out in front of the summation. Whatever variable is at the bottom of our sum, that's my index variable, which means I is the only thing that's a variable anywhere in here. N at the moment is not a variable. That 4 over n can pop out in front of our summation symbol. And I'm going to be left with this. If I distribute that minus sign in, then I'll end up with 2 minus 3, negative 1, and then minus 4i over n. Using another one of our summation rules, the sum of the sum is the sum of the sums. I can break this apart as 2 separate summations. I'm going to have the sum of negative 1 plus the sum of negative 4 over n times I. Both of those are still summations from I equals 1 to n. And now comes the fun part where I get to evaluate those sums using summation rules. This one right here says if I were writing that out, that's negative 1 plus negative 1 plus negative 1 plus negative 1 plus negative 1 n times, which makes this summation negative 1 times n. This part right here, with respect to my indexing variable I, the negative 4 over n is a constant and would come out in front of that summation. Which leaves us with the sum of I from 1 to n, and that's a formula that you are expected to memorize. And that's going to work out to be n times n plus 1 all over 2. Now for the fun part. I'm going to do this next part pretty quick because I know that it's almost 1 o'clock. So as I distribute that 4 over n in, on that first piece, my n's are going to cancel. I'm going to end up with negative 4. When I distribute the 4 over n into the second piece, oh, you know what? Let me clean this up first because that n and that n are going to cancel out. When I distribute that 4 over n in, I'll have 4 times negative 4, which would be negative 16 divided by 2. So I'm at negative 8. Still have that n plus 1 on top. And on the bottom, I'll have that n. Evaluating that limit, there's nowhere to plug the infinity in here. I just get negative 4. And as n approaches infinity, n plus 1 over n will go to 1. And I'd end up with minus 8, or a final answer of negative 12.